Okay, first thing is, if you haven't done your homework yet, there's a slight change to the assignment to match the videos. So I went and looked, and for this case, for some reason, the first section numbers were wrong. If you've already done them, that's fine. You can turn in what you did. But if you haven't done them yet, do these problems instead. It's like everybody's got them. So remember, this is since Kelly wasn't here last time. We kind of did this more difficult problem of trying to figure out how many numbers added up to 22. All the things that we did here was we showed all the different possible combinations of groups of people, rolls of dice, flips of coins, to be able to count how many occurrences there were. And so that's kind of tedious. If you're not interested in what are the combinations, but you're more interested in how many combinations. For example, using cards as an example, if you wanted to know, there's certain probabilities. If you're dealt a 5-card hand, the probabilities of getting certain hands. And the more complicated the hand, the less likely it is to get that hand, because the way you determine the probabilities is you figure out how many possible 5-card hands there are, and there are like 2.5 million different 5-card hands that you can get if you deal somebody at cards. And then you've got things that win. A 3 of a kind will be 2 of a kind, something like that. So, but getting 3 of a kind obviously is going to be more difficult than getting 2 of a kind. The question is, what is the actual probability of getting 2 of a kind versus 3 of a kind? You don't really care whether they're 2 aces or 2 5s. You're only caring whether they're 2 of a kind. I guess if you get 2 people who get 2 of a kind, then there's probably some kind of rule that says the higher card wins, but is the higher, whatever the higher ranking pair is. But in general, that doesn't happen very often. So most of the time, you're comparing one hand type versus another type hand, and so you have to count them. You want to know how many, 2 2s, 2 3s, 2 4s, and then different suits and all that kind of stuff. And so you're counting the number of hands. You don't care what they are when you're working on probabilities. So if we go to section 2, we'll start talking about how to do that. So there's a principle for counting things, and basically what these are multi-part processes. So if you are it's not dialing. What's that? Dealing. That's the word. Good think of it. Dealing cards. If you're dealing cards, the first step is you're going to pick one card randomly. You shuffle the card and you pick it. You take it off the top. It's a randomly determined card. There's 52 cards, and so you're going to pick one out of 52 cards, and then you'll get the next card, which there won't be 52 cards anymore. There'll be 51 cards, and so you'll have one out of 51 cards to choose from. And so the fundamental counting principle is used for multi-step processes, which we'll look at various ones of them, examples of them. So this is the question that I just posed. What if we're just interested in the number of possibilities rather than the exact choices? Then there's hopefully an easier way, and I'm not giving you time to write that down because I'm just saying it. You don't need to write it down. So there are the fundamental accounting principle is the next slide. To apply the fundamental accounting principle, you have to satisfy what's called the uniformity criterion for multiple part tasks. And let me just borrow your book for a second. For you people, for you guys who haven't had my class before, a lot of the stuff that I'm going to cover, I'm not going to ask you for word definition, and I don't want to make it so that you're writing so feverishly down stuff that you're not paying attention to the important points. So I may say, just reference that in your book, and you can go back later and look it up in your book instead of trying to write it all down. That's what books are for, as a reference. So, for example, this uniformity for most of the important stuff is in these little green boxes. So the uniformity criteria, we're going to talk about that, and then we'll talk about the fundamental accounting principle. So what I would suggest, if you're going to take notes, is just write down uniformity criteria or something like that. And then you might say, see book for definition or something like that. Now, a lot of times I'll actually just have the green box, and it'll be obvious that that's what you're going to do. In this case, I actually typed it out. I think it was because that was one of my first times I taught the class, and I decided to type it out. But yeah, these are both on page 534. So just reference. So let's read it. It says a multiple part task is said to satisfy the uniformity criterion if the number of choices for any particular part is the same no matter which choices were selected for the previous parts. So the key thing here is it says that the number of choices is the same. Obviously, say I want to pick 3 people for the class officers, Yeah, we're not doing class officers. It's a hypothetical thing. Okay, so let's say hypothetically that I'm choosing class officers. So, what's that? Yeah, I'm choosing you, and I must be choosing you as president, right? Because since he's the Trump guy, and Trump won president stuff. The Trump train. Yeah, that's it. Yeah, don't get in an airplane and start yelling at people comments about Trump. You might get kicked off. Okay. So how many people do we have in here? We have 8. We have 8 people. So, if we choose a president for the class, we have 8 people to choose from. So we'll pick Tanner for the president, hypothetically. And so then we pick the treasurer. And so the question is, we have, okay. Don't get distracted there. It's got to stay focused. Okay. You might want to move again away from that guy. He's distracting. Just you don't want to hurt his feelings. But anyway, so you choose one person out of 8, and so then you choose the treasurer. Well, you can't be treasurer and president at the same time. That's the rules. And so when you choose the treasurer for the next person, you have 7 people to choose from. So whether I choose Tanner or I choose James, it doesn't matter. When I choose the treasurer, I'm still going to only have 7 people. They're going to be 7 different people, but it's still 7 people. Yes? So your odds of being something increases as... Yeah, actually, that's true. If you look at that, the chances, if I randomly chose somebody, if we just pull names out of hats for that, then you would have, if once Tanner gets chosen as president, when you choose the president, it's 1 out of 8 possibility that you're going to be an officer. Once he's chosen, there's only 7, so to be treasurer would be 1 out of 7, and then secretary would be 1 out of 6. So as you go, it does increase the probability that you're going to be chosen in a random selection. Okay, so if the particular multi-part process satisfies the uniformity criterion, then you can use what's called the fundamental accounting principle. So it says when a task consists of k separate parts and satisfies the uniformity criterion, If the first part can be done in n sub 1 ways, the second part can be done then in n sub 2 ways, and so on through the kth part, so through the kth part of the multi-part process, which can be done in n sub k ways, then the total number of ways to complete the task is given by the product of each individual step. So that's a lot of words, so it's easier to just give a couple of examples. So here's a multi-part process. We're going to flip a coin 5 times, and we're going to write down what they are. You know, heads, tails, heads, tails, heads. So there's 5 things. And we want to know how many different ways can we have those heads and tails arranged. We did that in the previous section, but we did that by drawing a tree diagram, and then we took the tree diagram and we listed them all out, and we had a list of 16 different possibilities with 4 flips. So the answer for 5 flips is going to be 32, but how do we get that using the fundamental accounting principle? So let's define what these things are from the previous definition. So in this case, K equals 5. That's the number of parts in the process. So a part is a flip. Okay, 5 flips, K is equal to 5. So what we're going to do is we're going to say part 1. That's the first part is flip the coin. So that's the first time. So how many? So n. This is n sub k, n sub I. I guess I'll actually call it n sub I. So in this case, this is the first part. So I is the part number, the part. And you flip the coin. How many choices do I have? What's 2 options? Yeah. So n sub 1 equals 2. And part 2, I flip the coin again. So that's what the part consists of. Flip the coin, and so it's n sub 2 because it's the second part, and that also has 2. And so before we go any further, why does this particular process satisfy the uniformity criteria? It's because no matter if I flip the coin the first time, I have 2 options. If I flip the coin the second time, I still have 2 options. It's not like if I got heads the first time, I can't get heads anymore because it's just the same coin. So it's independent. The second flip is independent of what happens to the first flip. Okay, that's to remind me of something. But let me finish this problem first, and then we'll do it. Okay. So because this number, the number of choices, is independent of what happens the first time, then it satisfies the uniformity criteria. So that's the uniformity criteria. Okay, so part 3 is we flip the coin. So n sub 3 equals 2. Again, we have 2 choices, heads or tails. Part 4 is we flip the coin again, which is n sub 4 because it's the 4th step. And part 5, flip the coin. So the 5th step has 2 choices. So those are, and n sub k is n sub 5. So it says the kth part is the 5th part, which is the last one, can be done in so many ways. And it says the total number. Then the total number of ways to complete the task is given by the product of those individual values. So the total number of ways is equal to n sub 1 times n sub 2 times n sub 3 times n sub 4 times n sub 5. And those are 2 times 2 times 2 times 2 times 2, which is 32. Therefore, there are 32 ways to, or 32 arrangements of heads and tails from flipping a coin five times. Why do we use a coin in a lot of these examples? Because, you know, we know what coins are. It's a random process, and it's got a simple result to it. So it's used a lot just because it's a way of demonstrating things. It's not like there's a lot of usefulness in flipping coins. You know, normally we flip a coin one time, and we're choosing between two people. We don't. But it actually has. I think we talked about this last semester. I mean, flipping a coin, there's two options. There's heads or tails, which has an analogy with ones and zeros as far as computers are concerned. So the things that we do with coins can be used ultimately, theoretically, for flipping for computer stuff. Okay. Before I do the thing I had set my alarm for, let's just do one more example. So how many ways can you group 5 people where order is important? So what I'm talking about is what we would do is we put 5 chairs up here in front of the room, say. And we have 5 people. And I want to just, you know, we're going to have some kind of class, 5-person class portrait. And the question is, how many ways can you arrange those 5 people in those 5 chairs? So that's the basic idea. We're not taking 5 people and picking 3. We're taking 5 people. We're sticking in 5 different chairs. So let's do it here. So again, you break this up into a multi-part process. So let me just put some little, these are just represent chairs, okay? So if you were going to fill up these chairs, rather than just randomly saying everybody run for a chair, you want to do this in some controlled manner. And so what you could do is you could have a hat with the names of 5 people in it, and you could shake it up, and you would pick one out, and so one of those 5 people would get the first chair. So so the 5-part process, we have another 5-part process here. So let's do the same kind of thing. Part, number, we'll put task, what are we doing? Number of choices. Okay, so task number 1 is to choose one of 5 people to sit in the first chair. Okay, so we're going to put somebody into the first chair. Well, how many people do I have to choose from when I make that choice? 5. Okay, so somebody's in there. I'm not going to put a letter. Okay, part 2 is choose one of 4 people to sit in the second chair. So how many choices do I have at that point? 4. Why do I have 4 choices instead of 5 choices? Yeah, the first person's already sitting down, so you can't choose the second person. I mean, you can't use them. They can't sit in 2 chairs at one time. Okay. So you can see how this thing's going to work, is that every time we put somebody in the next chair. So the third step is choose one of 3 people to sit in the third chair. And I don't know why I'm going between writing it out in words, but I am. So there's 3 people, and you can see the next. This is going to be The fourth step, there's going to be 2 people on the fifth step, so I'm just going to kind of say ditto. It's not exactly copying, but it's hopefully you understand it. So, so from our case, you know, n sub 1 is 5, n sub 2 is 4 because I have 4 choices when I pick the second. N sub 3 is 3, n sub 4 is 2, n sub 1, and n sub 5 is 1, and therefore the total number of arrangements is equal to n1 times n2 times n3 times n4 times n5, which is, we just did above, 5 times 4 times 3 times 2 times 1, which is 120. So there are 120 different ways that you can arrange 5 people and it be the unique arrangement. Okay, so that's how the fundamental counting principle works. You just have to think about the process. Sometimes sometimes the questions they ask can be difficult just based on, you know, how they're asking. You know, sometimes you get it and sometimes you don't, as far as trying to understand what the different processes are. Well, when we get to those, you'll see. The ones that you'll have to do for tests are not that difficult, relatively speaking, but we'll look at ones that are more difficult. Okay, so that is, we're going to stop for just a second. So part of, got to push the record button earlier, so that's okay. So I'm going to make, I do make political comments, and I made this the other day in the other class. So one thing I don't talk about, but you know, in terms of sexual assault, there's the question of, you know, did somebody ask for it or not, because of the wearing the provocative clothing, which in the United States is not that, you know, the culture is such that that's not, shouldn't be a reasonable excuse. But in some other more conservative countries, Islamic countries, you know, they're going to say, you know, if you dress and you know you're not in your burqa, that, you know, you're asking for anything that you get. So that's, you know, that's one thing you hear a lot about. So I heard this thing the other day that made me think relative to that was the Russian hacking of the DNC. So you know, they finally said, oh yeah, I agree that the Russians did hack the DNC, and yeah, they did, and as a result they helped Trump a little bit. How much, we don't know. And so what you get is some of the Republicans saying, well, the problem was that the DNC didn't have strong enough, they just didn't work hard enough on security, so it's their fault. It's not the Russians' fault for hacking, it's the DNC for, so it's kind of like blaming the victim, which was the DNC, the Democratic National Committee. It's your fault because you didn't protect yourself enough, not because you dressed too scantily. But it's not the Russians' fault for doing the crime in the first place. So that's that was my is that what? Yeah. So anyway, that was my political thought. Really, it was before I saw the video, and I thought, oh, yeah, that's okay. So it turns out that in these counting situations, we have this case where we multiply numbers together, where you multiply a number and then the next smaller number, then the next smaller number, the next smaller number. And so we have a special math function for that. It's called the factorial. So the factorial formula for any counting number n, so it's an inch, you know, something you can count on your fingers, so no decimals. The quantity n factorial is given as follows. So if you see n factorial, it's the same as seeing the number n multiplied by the number smaller than that by the number smaller than that, all the way down until you get to 1. So the formula here looks kind of complicated, but the reality of the situation is not that complicated. So if you have 2 factorial, what that means, it's equivalent to 2 times 1. So you start at the value n. N is 1 in this case. I mean, it's 2 in this case. N minus 1 is 1. You go down till you get to 1, and then you're done. And so then you can also say this is equivalent to 2. 2 times 1 is 2. So 4 factorial is 4 times 3 times 2 times 1. And that's equivalent to 24. 7 factorial will be 7 times 6 times 5 times 4 times 3 times 2 times 1, which is a big number. It's actually, I remember it from yesterday, it's 5,040. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is a big number, which I'll write down here. So 10 factorial is 628,800. So that's 10 factorial. Interestingly enough, I mean, this calculator has factorial on it, but it's not directly on the front screen. So you have to go through about 4 levels. And I found out that it's easier to not use factorials, which I'm going to teach you how to do. So if your calculator doesn't have factorials, you'll be fine. You don't have to buy a calculator to do factorials. Yes? Where? Oh, this one? 2 times 1. Yep. So don't worry if you don't have factorial on your calculator. It does help in terms of not having to write out a lot of numbers, ultimately, but in terms of actually calculating it. There are other places that choose factorial, and so my old calculator, I told the story yesterday, you know, you guys grew up with calculators, probably used this in high school. You know, you got your cell phone that does all kind of good stuff. When I was in high school, well, first year I was a student at Virginia Tech in engineering. It was the first year that they required calculators. So the previous year, you could have calculators, but you weren't required to have them. And you could use a slide rule, which is another way of multiplying and dividing numbers together, but it's not as accurate. So the calculator we had to buy cost $100. And it does what probably a $1 calculator, but if you buy those TI-31s, they're about $10. But in terms of today's dollars, it's probably $100 back then is probably $300 now. So to do what a $1 calculator does now, it would have cost $300 back then. That was a big investment. I looked it up yesterday. So let me just show you what the calculator looked like. And it was actually a step up. My wife had, she wasn't my wife at the time, but we went to high school together. She had a calculator that did plus minus, multiply, divide, and take a square root. That was the 5 functions that it had. Actually, it did a reasonable amount of stuff. It did logarithms, exponentials, it did factorials. That was the thing, which was important. We use factorials anyway. 1 factorial is 1, and 0 factorial is 1. So the 0 factorial is the one that you wouldn't, you know, why is 0 factorial 1? And it's just because it works in the formulas. So if you have a formula that involves factorials and you get a 0 factorial, to get things to work out, it has to be 1. There's no other good explanation of why 0 factorial is 1, because 0 times anything is 0. So, but okay. So, well, it turns out that in this class we're going to most of the time, we're going to evaluate the ratio of factorials. And if you have factorial on your calculator and it's easy to get to, you probably would just use the factorial. But because my calculator takes 5 steps to get to the factorial button, it's sometimes easier to do it a different way. And if you don't have factorial in your calculator, then you can use this way to solve it. So if I have an equation that gives me this result, 9 factorial divided by 7 factorial, how do I make that a simpler calculation? Because, you know, for this case, I'm going to just write everything out, and then I'm going to show you how you would make it so that it is not as complicated. So 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. So what you can see is that I can cancel out all this stuff with that. And 9 times 8 is 72. So the answer here is 72. And ultimately, all I had to do is multiply 2 numbers together. If I use just factorials, I have to multiply 9 numbers together and divide by 7 numbers together, which would be a pain in the neck. So what we can do is we can take the original factorial and you start the factorial process, but you can stop at any number and then just put the factorial sign. So 9 factorial is 9 times 8 times 7 factorial. And therefore, my cursor's acting a little weird there for a second. So then I can divide by 7 factorial. And I can cancel those out because of the same thing. And you just end up with 9 times 8, which is 72. So ultimately, it would be easier for me to take this, convert it to that, and then just multiply 9 times 8 rather than having to go through my calculator to get to factorial. And that's the way you would do it to not have to use factorials in your calculator. Yes.
So if your 7 factorial is above your 9 factorial,
Yes. Yeah. Typically in our calculations, the larger factorial will always be in the numerator. So technically you're correct. You won't see that happening, but it would be true. Okay, so let's just look at a couple of other examples. And actually I'm going to I'm going to simplify, do one that's not quite as hard. So let's say we have 13 factorial over 10 factorial. So what we would do is we would take 13 factorial and make that into 13 times 12 times 11 times 10 factorial. And I choose where I stop based on what I'm trying to cancel out in the denominator. So those cancel out. And then I just multiplied the 3 remaining numbers together. So 13 times 12 times 11 is 1,716. So let me give you one to work on. So for you guys online to see that you're actually paying attention, let's do 17 factorial over 14 factorial. And once you get an answer online, if you can raise your hand so I can hear you all. And you might get to the point where you don't even have to write it out, right? For some of you, you'll say, yeah. Some of you will say, I don't get it yet. But, you know, for example, while you're working on this one, you know, if I saw this, I'd say, well, all I have to do is take 13 times 12 times 11. I've got the answer. You know, all the canceling out, I would just do kind of. Would
that offend you on the test?
Would it offend me?
Yeah.
If you just wrote out 13 times 12. I want you to show some. I don't want you to just show a number. So even if you have factorial, I don't want you to use it. But if you wrote 13 factorial over 10 factorial is equal to 13 times 12 times 11, I would be fine with that because I know that you know what you're doing. So let's see if anybody's answered online. Yep. Okay, we got 3 answers. So they're saying 4,080. You guys agree with it? Yeah, so I'm assuming it's right, and it is right. Okay, so what we're doing, just in case you didn't get it, we took 17 times 16 times 15 times 14 factorial divided by 14 factorial. And so you have 17 times 16 times 15, which is 4,080. And some people get carried away with simplifying factorial stuff because they'll do something like 6 factorial divided by 3 factorial equals 2 factorial. Because they think, oh, 6 divided by 3 is 2. So 6 factorial divided by 3 factorial is 2 factorial. And that's wrong. Okay? The only time you can do any kind of math with factorials is when they're exactly the same thing. So if I were to rewrite that as 6 times 5 times 4 times 3 factorial divided by 3 factorial, then I could do it. So that is incorrect. I've seen it too many times. So I'm trying to emphasize this is a problem. That is not right. What you would do, if you took 6 factorial over 3 factorial, you would have 6 times 5 times 4 times 3 factorial divided by 3 factorial. That's the only, and those cancel out. That's not telling you it's wrong. So the answer would be 120, not 2. You'd be way off if you...
So your attendance question is going to be to evaluate the following ratio of factorials. So let's do 11 factorial divided by 6 factorial. And the answer you can use as your attendance question for class 2.
Okay. So now that we've defined factorial, it turns out that the arrangements of n distinct objects, that's the problem where we had 5 people and we stuck them in 5 slots, in 5 chairs. And we looked at the different, there were 120, I think it was. Is that right? I think it was. 5 times 4 times 3 times 2 times 1. And let's just go back here. When we did this problem, we hadn't defined factorials, but we basically did 5 factorial. Okay. So this kind of a situation happens enough that we have a rule which says that the total number of different ways to arrange n distinct objects is n factorial. So if I had 3 objects, A, B, and C, in this case, n is the number of objects. So they could be letters, it could be numbers, it could be people. So what we can say is we can arrange A, B, and C in 3 factorial ways because there are 3 of these. And 3 factorial is 3 times 2 times 1, which is 6. So the answer is 6. And we could do a tree diagram, and you would confirm that it's 6. But it's a lot easier to take 3, to count the number of things, and apply the factorial function to it and get the answer instead of writing out the tree. I'm going to write out the tree. You don't need to write it down if you don't want to. But let me show you how you would do it as a tree diagram. And I'll say, first step is to pick the first object. The second step is to pick the second object. So just like we were doing earlier, there are 3 possibilities to pick when you pick the first object. Once you pick A, then you only have B and C to choose from. If you pick B, then you only have, for the second choice, you only have A and C to choose from. And if you pick C first, you only have A and B to choose from. And then when you pick the third one, well, there's only one person left over. So the one that's left over is the one I'm showing here. If I'm doing this right. And from this tree diagram, I could list all possibilities, which would be A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. And then I'd count 1, 2, 3, 4, 5, 6. and I'd say there's 6. Obviously, taking 3 factorial is a lot easier than going through this whole process of doing a tree diagram, but that's okay, so that's that. So the question might be, if I have 26 letters in the alphabet and I arrange all those 26, so if I had how many 26, if I wanted to have a 26 letter word with every letter being different, how many different words could I create? It's kind of like also if if you think about, well, that's not true. I was going to say something like license plates, or where you have to use numbers and letters. We'll be able to figure that out in a minute, but it doesn't work. It's not a simple factorial thing. So if you wanted to arrange 26 letters, using all 26 letters, but not reusing any of the letters, not repeating any of the letters, the number of arrangements of a 26 letter word with no repeats, the answer would be 26 factorial. So 26 factorial is a big number. I just want to give you an idea of how many different arrangements you can have. So you can arrange those 26 letters 4.03 times 10 to the 26th. What that means is basically 4 with 26 zeros, which would be a very long number, which would be more stars than are in the universe or something, probably. So once you get to a large number of letters like that, choices, you can have a huge amount of arrangements. We already did this one. 5 factorial. How many ways can you arrange the letters A, B, C, and D? There are 5 letters, so the total number of arrangements would be 5 factorial. So I'm not going to repeat that one. We've already done it. And then the final part of this chapter is if we had letters and we wanted to rearrange the letters, but we have repeats of the letters. So I'm going to show you an example, and then we'll look at the formula. So here's a name. It's my name. Which has a repeated letter if I use, well, I guess it depends, no matter how I spell it, you have 2 E's. So Steve, there's the first E and there's the second E. But if I were to switch this E with that E, it would still be Steve. It's still the same word. And you wouldn't be able to distinguish it if I didn't put those little subscripts on there. So what I would say is, if I took both of these and I had Steve, and if I would put my second E first and my first E second, these, if I don't put the subscripts, they're going to look the same. They're still Steve. So these two are indistinguishable. So what it says is the number of distinguishable arrangements. So you eliminate, if you have two that are indistinguishable, you only count them one time. So the number of distinguishable arrangements of n objects where one or more subsets consist of lookalikes. Lookalikes are repeat. Say n1 are one kind. In this case, I only have one. I have a repeat of E. So forth and so on. The total number of distinguishable arrangements is n factorial. N is the total number of letters. N1 would be the letter that I repeat. So I have 2 E's that I repeat. So for my example, N is equal to 5. That's the total number of letters. N1 equals 2. There are 2 E's. So the total number of arrangements, total number of distinguishable arrangements, is 5 factorial divided by 2 factorial. So here we have this ratio of factorials. So we could rewrite the numerator as 5 times 4 times 3 times 2 factorial and divide by 2 factorial. So that's not 1, that's factorial. So these cancel out, and so you'd have 5 times 4 times 3, which is 60. So there are 60 ways that you can arrange these 5 letters that are distinguishable from each other. If you had 5 different letters, the answer would be 120. So the thing is, anytime you have these 2 E's, you can have them in one place, so you can flip them. So you lose half of your arrangements, because there's always going to be another one that from your original 120, there's always going to be one that matches up with the E's. You can just switch. Okay, so that one's pretty easy. Let's look at one that's here's a word. If it's a word, it doesn't have to be a word. So for this particular case, n equals 6, because I have 6 letters. I'm going to say G is, the letter G will associate with n sub 1. There are 2 G's, and the O's, which we'll call the second subscript, there's 3 O's. So the number of arrangements is going to be 6 factorial n divided by 2 factorial n sub 1 divided by 3 factorial. And that's not 0. You can't do it, and again, you can't, 2 factorial times 3 factorial does not equal 6 factorial. So what I would probably do to simplify this, I'd go 6 times 5 times 4 times 3 factorial. So I'm changing the numerator to this so that I can cancel out the 3 factorial that I have in the denominator. And so I get 120. 6 times 5 is 30. 30 times 4 is 120. 120 divided by 2, so I get 60. So the answer is 60 again, coincidentally. So there are 60 ways that I can arrange these 6 letters, 2 G's, 3 O's, and an L, such that they're distinguishable from each other. Yeah. Right here? What I did is I rewrote 6 factorial as 6 times 5 times 4 times 3 factorial, so that I could cancel out this 3 factorial with the other 3 factorial. I mean, it wouldn't have been that much work to just write them out and do them separately, but it's just a habit that you might want to get into. So then these cancel out, so you're left with 6 times 5 times 4 divided by 2 times 1. Okay, so let me give you the homework assignment. So we're going to assign this section homework. This will be due next Thursday. So there's the homework. So then we've got one more example that we'll work on next Wednesday, next Tuesday. Remember, you don't have school Monday. It's Martin Luther King Day. Next Thursday. So make sure you do your homework. Do it on time. If you've taken a class before, probably one of the reasons you're taking the class again is you didn't do your homework. So don't repeat. Don't define what is the definition of insanity. Do the same thing and think you'll get a different result. You won't. So if someone who hasn't turned in homework in the past continues not to do that, I'm gonna hound you. Well, I didn't hound them last time. I'm gonna get a big stick and start beating them if they don't. No, I can't do that. But anyway, we'll see y'all later online. So you can hang up now. So let me know if you're actually paying attention.